Various flip-flop in various categories are listed here. They are either SR flip-flops. They can be clocked SR flip-flop. Clocked SR flip-flop can be further classified as level triggered flip-flop or age triggered flip-flop. Age triggered flip-flop can be positive age triggered or negative age triggered. They can be JK flip-flops. They can be master slave JK flip-flop. They can be T flip-flop and they can be D flip-flop. T flip-flop is also called as toggle flip-flop and D flip-flops are called as data flip-flop. T flip-flop toggles the state on every edge, say positive edge of the clock, and therefore they toggles in every cycle on positive edge of the clock. D flip-flop latches the data input at the output when the clock is applied and definitely indefinitely hold the data at the output as long as no next clock is applied. Let us see the implementation of the SR flip-flop using NAND gate and NOR gate. First we will see using NOR gate. It consists of two NOR gates. The inputs marked as R input and S input to the two NOR gate here. And the output of first NOR gate is cross coupled to the second input of lower NOR gate, and the output of second NOR gate is connected to the second input of first NOR gate. The R input is also called as reset input and S input is called as set input. That's why the name of the flip-flop is SR flip-flop. The output of the flip-flop will be always one output is Q and another output is the complement of Q. The expression for this Q output and Q bar output from the NOR gate operation is shown here. So Q output is complement of R or Q bar and Q bar output is complement of S or Q. So these are the expressions, logical expression for the outputs of the flip-flop. Let us see the operation of SR flip-flop. Let us assume that the initial condition is Q equal to 0. So obviously Q bar equal to 1. When power is first time applied to the flip-flop. Let us consider the first case now. S is equal to 1 and R equal to 0. So we apply, make S is equal to 1 here and R equal to 0. So when S is 1 and R is 0, it is called set mode. So see here, when S is equal to 1, consider the lower NOR gate. So it is not OR. Consider this gate as OR and NOT. So when S is equal to 1, the OR operation output is 1 and complement of it, that is 0. Therefore, Q bar equal to 0. Shown here. When S equal to 1, Q bar will be pulled to 0. When Q bar will be pulled to 0, the second input of the first NOR gate is going to 0 and R is already 0. So both the inputs to this NOR gate are 0. So therefore output of the NOR gate is 0 or 0 complement, that is 1, and therefore Q becomes 1 and Q bar becomes 0. Now consider the second case. When we make S is equal to 0 and R equal to 1. Means we want to reset the flip-flop. When R equal to 1, here the first NOR gate output is 0 And when this output is dropping, that is connected to the input of second NOR gate. S is already 0 and this Q output is also going to 0. And therefore, the lower NOR gate output is 0 or 0 complement, and therefore Q bar output is going to 1. And therefore, when R is equal to 1 and S equal to 0, Q output will be 0 and Q bar output is 1. So by making reset input R in logic 1 state, you can reset the output Q to 0. Setting of output means setting it to the logic state 1, and resetting the output means setting it to the logic 0 state. Consider the condition 3. In condition 3, suppose both S and R both are 0. When both are 0, there is no change in the output because the output depends on the previous state of Q and Q bar. So output doesn't change when S and R inputs are same. Let us consider the fourth condition now. When S equal to 1 and R equal to 1 means we want to simultaneously set the output as well as reset the output, and therefore this input combination is an unstable state, and therefore this should not occur in the operation of SR flip-flop. This should be avoided. Otherwise, the circuit goes in the race around condition. Both the output tries to become one, and that is not possible. And therefore, S and R inputs, when both are 1, this condition should be avoided in practice. And therefore, now we will show this SR flip-flop by its symbol. The flip-flop is normally shown by a square box with two inputs S and R and two outputs Q and Q bar. The truth table of the SR flip-flop shown here. Those are the condition of S and R inputs and corresponding output Q and Q bar. And we have seen all the four conditions of S and R inputs. We will fill up this table. When both S and R inputs are 0, the output Q and Q bar remains in the last state. There is no change in output. When R input is 1 and S input is 0, the flip-flop output will be resetted, means Q becomes 0 and Q bar becomes 1. When S input is 1 and R input is 0, we are setting the flip-flop, and therefore Q output will be set to 1 and Q bar output will be 0. This is called set state. When both the inputs are 1, this condition should be avoided because this is called the race around condition. When this condition occurs, there will be race in the output to become 1 simultaneously. And therefore, the logic operation of cross-coupled inverter fails. And therefore, this condition should be avoided. Here, the next figure shows the SR flip-flop using NAND gate. Two NAND gates are used. R and S inputs are connected to gate 1 and gate 2 respectively. And Q bar output of second gate is cross-coupled to another input of first NAND gate, and Q output of first NAND gate is cross-coupled to second input of the second NAND gate. The truth table is again same. You can verify from this circuit. When S and R both are 0, there is a race condition now. And therefore, this condition should be avoided in this implementation of the flip-flop. When both the inputs are 0, this NAND gate tries to make the output Q and Q bar both tries to go to 1. And therefore, this is a race condition between the two outputs and therefore should be avoided. When S is equal to 0 and R is equal to 1, Here you will get the flip-flop. So you will see when the set out input is 0, the flip-flop output Q will be resetted, and when the reset input is 0, the Q output is set. So there is a complement of this operation takes place compared to the flip-flop implementation using NOR gate. When both the inputs are in logic 1 state, there is no change in output. So flip-flop changes the state when S and R inputs are dissimilar. In this case, the flip-flop can be set or reset by using logic 0 as input. So consider the second row again. When the set input S is 0, the Q output will be 0. So flip-flop will be resetted by using set input 0. And when you have the reset input 0, you will get Q bar output resetted to 0 and Q output becomes 1. So therefore, note the difference between the output between the NAND gate implementation of the SR flip-flop and NOR gate implementation of the SR flip-flop. Now, in general, if we focus on the NOR gate implementation of the SR flip-flop, we have to remember just that when the set input is 1, the Q output will be set to 1. When reset input is 1, the Q output will be resetted. That is for the SR flip-flop using NOR gate. Now, various triggering method used for the flip-flops. We have already discussed this, but let us review it again. The flip-flops can be level triggered flip-flops or they can be edge triggered flip-flop. Means if the flip-flop is changing the state in this positive level here when the clock is logic 1, then it is called positive level or high level triggered flip-flop. Whenever the flip-flop changes the state during low state of the clock, then it is called as negative level or low level triggered flip-flop. Whereas if your flip-flop changes the state on positive edge of the clock only, then it is called positive edge or leading edge triggered flip-flop. Or if your flip-flop is changing the state on falling edge of the clock, it is called as falling edge triggered or trailing edge triggered or negative edge triggered flip-flop. Let us see how clock can be added with the flip-flop. Let us see the NAND implementation of the flip-flop. With this NAND gate implementation of the flip-flop, let us denote the input to the basic SR flip-flop as S dash and R dash. And S and R inputs are additionally passes through the two NAND gates and they are individually ANDed with the clock input. So R dash and S dash input of the first level of the gates depends on the state of the clock, whether it is in high state or in low state. The symbol of the flip-flops are shown here. The first circuit is a SR flip-flop with positive level triggered. Here there is no bubble. In negative level triggered, there is a bubble on the clock input. So if you see these two, we have added the third input in the SR flip-flop, that is clock input CK. Whereas in the third diagram, this one, there is a triangle symbol shown. This indicates the flip-flop outputs depends on the clock input positive edge. So it is called as positive edge triggered flip-flop. And if there is a bubble shown here with a triangle, then it is a negative edge triggered flip-flop. The edge triggered flip-flop output doesn't change for the constant input level either in high state or low state. The age triggered flip-flops are only changing the status of the output on edges. The truth table of the SR flip-flop with clock is shown as a third input. Say when clock is altogether 0, then S input can be don't care, R input can be don't care. Means this cross indicates the don't care input. Don't care means it can be either 0 or 1. It doesn't have any effect. That is indicated by the cross sign. So when clock is 0 and S and R both are in don't care condition, the output of the SR flip-flop remains constant in the previous state. So there is no change in the output Q and Q bar. When clock is 1 and S and R both are 1, then also there is no change in the output. When clock is 1 and R input is 1, the Q output will be 0 and Q bar output will be 1. This is using NAND implementation. When you use the NOR gate implementation, then when S input is 1 and R input is 0, the Q output will be 1 and Q bar output will be 0. Okay. Now consider the third row when clock is 1, S input is 1 and R input is 0. The flip-flop will be going in the set condition. When clock input is 1 and both S and R both are 1, then there is a race between the output and therefore this is the condition which is unstable condition and therefore this should be avoided. So if you see the first four conditions, when clock is present, clock is absent means it is 0, there is no change on output. When clock is present but both the inputs are 0, then also there is no change in output. And if you see the third row, the flip-flop will be resetted when clock is positive as well as reset input will be 1. Flip-flop resetted means Q output will be 0 and Q bar output will be 1. Whereas if you consider the next row, when clock is 1 and S input is 1, this flip-flop will be, output will be set to 1. And therefore, obviously Q bar output will be complement of Q, that is 0. Set and reset words are normally reference to Q output. When we say that the specific input combination sets the flip-flop, means it will set the output to logic 1 state. Same is for reset. When we say that flip-flop is in reset state, means Q output of the flip-flop will be in reset state, means 0 state. Limitations of SR flip-flop. SR flip-flops, whenever they are level triggered, they are suffered from race condition, means they will toggle more than once as long as the clock level is present at the clock input. And therefore, this race around condition can be avoided by converting the SR flip-flop to JK flip-flop or D flip-flop. Let us see simple D flip-flop. In D flip-flop, our SR flip-flop is used using 4 gates. Gate 1 and gate 2 is a basic SR flip-flop. Gate 3 and gate 4 is basically adding the clock input, and the data input D is directly connected to the S input of the flip-flop circuit, and complement of D is used as reset input to the flip-flop. The symbol of D flip-flop is shown here. There is a single input D and Q output and Q bar output, and there is a clock. If there is no bubble on the clock, it is a level triggered flip-flop. If there is a triangle on the clock input, then it is a edge triggered flip-flop. Now here you will see there is a triangle in the symbol, means this is a positive age triggered flip-flop. If there is a triangle and bubble present on the clock, it becomes a negative triggered flip-flop. If there is no triangle, then it can be positive age triggered. And if bubble is present, as shown here, if bubble is present only, then it is a negative level triggered flip-flop. The truth table of D flip-flop is shown here. Now there are two inputs to the D flip-flop as shown in this figure, the D input and clock input. When clock input is 0, it is say disabled. When clock is 0, the data input is ineffective, means whether it is 0 or 1, it doesn't affect the output of the D flip-flop. When clock is 1 and data input D is 0, then this clock will reset the Q output, means it will set the data input at the Q output, means Q output becomes same as the data input. Now, when clock is 1 and data input D is 1, then output will be set. So from last two rows, you will see that as long as the clock is present, the D output will be reflected at Q and complement of D is available at Q bar. So ultimately we are saying that this clock will store the condition of data input in the flip-flop. Once the data output of the flip-flop is changed, and if we remove the clock from the flip-flop, the output remains in the same state indefinitely as long as the clock is not again made in the logic 1 state. And that's why this flip-flop is called as the data flip-flop, which latches the data input when the clock is in the asserted condition. Now, the JK flip-flop implementation with positive age triggering is shown here. Again, if you see what is the difference, gate 1 and gate 2 is basic SR flip-flop having input R dash and S dash. Gate 3 and gate 4, they can add the clock input with the two external input. Now they are renamed as J and K. And additionally, in this JK flip-flop, the Q output is cross-coupled as a third input to gate 4, means that is ended with the clock again. And Q bar output of the lower gate number 2 is cross-coupled to the third input of the gate 3, that is ended with clock and J input. The truth table of the symbol of JK flip-flop is shown. Now, if you see here, the additional circuit using capacitance and resistance with a diode is shown. Here, this capacitance and resistance R1 is forming a differentiator circuit, which will convert the square wave clock signal into spikes, differentiated spike. So, output of the differentiator circuit can have only positive spike at positive edge and negative spike at negative edge. Whereas negative spikes means negative voltages are not applied to our logic circuit. We add a diode which rectifies this positive and negative spike, and output only consists of positive spikes. And these positive spikes can be used as a clock. And thus, we have converted a basic SR flip-flop to JK flip-flop with clock age triggering. The output expression from this circuit can be written as the S dash output, that is the intermediate output, is K, Q and clock complement, and R dash input to basic SR flip-flop is J, Q bar and clock complement. That is basically the NAND operation. You can very well see here. K, clock and Q. That is the AND operation with a complement of by using 4 gate number 4. And this R is, see here, J, Q bar and clock and complement by this inverter. So J, Q bar and clock complement will be R dash. Remaining operation of gate number 1 and 2 is same as general SR flip-flop using NAND gate we have already seen. So let us see the truth table. Now we have clock input, J input and K inputs. Also, we will see that we have cross coupling of Q output and Q bar output. And therefore, Qn plus 1 and Qn plus 1 complement, these two outputs are also taken in consideration. Qn plus 1 is the next state of the flip-flop outputs when the input conditions are changed. Now let us see the case 1. When clock is 0 or 1, means if it is having any state, if J and K both the inputs are 0. See here, when J is 0 and K is 0, this is a NAND gate operation. So AND gate gives here 0, complement of it gives 1. So R dash becomes 1 and S dash is also becomes 1. And when R dash and S dash both are 1, then there is no change in the output. We have seen the truth table of SR flip-flop using NAND gate. And therefore, there is no change in Q and Q bar. Consider the second case. Now, if the clock is going down, see here, in our circuit, our flip-flop is only positive edge triggered because we clip the all negative edges and only positive edges are applied. So when clock is going down, there is J and K input in either 0 or 1 state. There is no change in the output because clock is not at all reaching to the gate 3 and 4. And therefore, their output R dash and S dash never changes. And therefore, there is no change in Q and Q bar output again. Third case, when J and K input itself are 0 and clock can be going high, then also there is no change in the output because R dash and S dash inputs are both are in logic 1 state. When they are in logic 1 state, there is no change in the output of the flip-flop using NAND gate 1 and NAND gate 2. The next state that you can very well verify here. Consider J as 0. What is the output of this NAND gate 3? Consider this not AND or AND not. So 0 is ANDed with anything is 0 and not of it. So it is 1. So R dash is 1. Similarly, S dash is 1. And if you refer the truth table of SR flip-flop using NAND gate, when both the inputs are 1, the output will not be changed. Now consider the very important state, that is the fourth state. When J is 0 and K is 1 and clock is also rising from 0 to 1. Then let us assume temporarily that clock is 1, J input is 0, and when J input is 0, definitely R dash input is in logic 1 state. Whereas consider the 4 gate, K is 1, clock is 1, and Q is also 1. So S dash input is in the